Well, a warm welcome indeed to everybody joining. Thank you for being here. Grab yourself a notebook, pencil, or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you out of nowhere. Today, we have a pretty good problem. Interesting situation. It's about heating up a wire. It's from the 2005 BC AP Calc BC exam. Now, that being said, if you're in AB, you could approach this problem still, so don't feel discouraged. If you know your calculus well enough and you're in AB, you can totally do this. Yeah. Okay. Give yourself some time, maybe about 12-ish to 15 minutes, to work on this on your own. Pause the video, read through everything you need to, give it a shot. And then when you're ready, come back and see if you were thinking about this right. Particularly, part D is an interesting little thought experiment. Okay, let's go. Looking at this table, we see the temperature. The temperature's fluctuating. It's going down. So I'm tempted to think it's over time, but then I see this says distance. So I'm like, what? What do you mean distance? Let's read the question. A metal wire of length 8 centimeters is heated on one end. Okay? Only on one side of the wire. The table above gives selected values of the temperature, T, of the wire, X centimeters from the heated end. Got it. So the part where we're directly heating it, this is how hot the wire is. And then as you move down the wire, like away from the end where it's getting hot, you see that this is changing here. Yeah, so when we're all the way on the other end of the wire, it's 55 degrees Celsius, whereas it's 100 degrees Celsius on the part where we're heating it. Okay, I think we understand this now. So as we go further out, the temperature changes. Estimate T prime. That's part A. Estimate T prime of 7. Show your work that leads to your answer. Indicate units of measure. Well, T prime, that just means derivative, right? How do we estimate the derivative? Well, we don't have the exact function, so we can't take a derivative, but derivative also means slope. So we're going to find an average slope, because that's the best we can do to getting a slope at 7, is taking the average slope from here. So we're going to say, I guess we can write it in here, we can say T of 8 minus T of 6, oops, let me close my parentheses, over 8 minus 6. So how hot it is at 8, that's 55, minus how hot it is at 6, that's 62. So 55 minus 62 is negative 7, over 8 minus 6 is 2. So we say about negative 3.5, and this is going to be degrees Celsius per centimeter. So that means, like, as you're moving along the wire, pretend that there's a wire, and as you're moving along it, here's the part where it's getting like super hot. As you're moving along it, then at this moment, as you're moving, the temperature is overall changing 3.5 degrees Celsius per centimeter at that exact moment. The temperature is dropping, a lot more in certain spots. Like, as it's further, the temperature drop might be different. You'll notice that here, the temperature is dropping by 8. So let me put that in red, actually. So from seconds 5 to seconds 6, that's minus 8. And then it takes 2 centimeters, notice this is 2 centimeters, to drop by 7. So it seems like the temperature drop is more significant over here. Who knows, though? Kind of interesting, because from 0 to 1, it's a 7 degree Celsius temperature drop in 1 centimeter. So maybe my rambling thoughts are not spot on about that. Okay, in any event, that is what the derivative represents. As you're moving along the wire away from the heated end, the temperature is changing about 3.5 degrees per centimeter. Okay, let's talk about part B. It says write an integral expression in terms of T for the average temperature of the wire. Estimate the average temperature using a trapezoidal sum. Okay, so that's actually a thing we're going to get points on. Using 4 subintervals that are given by the data and indicate units of measure. Okay, so this is going to take a little while. If you gave yourself 15 minutes, that's totally fine. First, let's talk about the integral expression. We're going to approximate the average temperature, because average temperature, we use this formula, 1 over b minus a. Sometimes people put it like that, or you can just put it all over b minus a. Integral from a to b of f of x. I guess I'll put t of x dx. That's the average. It's like the formula kind of for finding the average value. And then we want to estimate it. So I guess we would put integral, it would be like 1 over 8. Integral from 0 to 8 of t of x. That is the average value. Now, since we don't have a specific function for t of x, like we just have a few data points, we're going to have to approximate this integral. So here's where the trapezoid approximation comes into play. So we're going to do that up here where all the data values are at, remembering that we make the trapezoids, I'll sort of represent it kind of like on a graph. We have a height of 100, and then we have a height of 93, which is not as high, and then later on at 5, we have a height at 70, and then we have a height at 62. Oh, actually, that's a little drop of 8. And then at 8, we have 55, so something like that. So our trapezoids are going to look like this. Right? And so that means that our trapezoids are going to follow this trapezoid formula. You got to know the trapezoid area formula. Let me move this up a little bit. There we go. So we're going to get 100, base 1 plus base 2, over 2, times the height, which is 1, plus this height is 4. Let's see, so we're going to have 93 plus 70 over 2, and then times 4, plus the next one is going to be 70 plus 62 over 2 times the width, which is technically the height here. The height along the bottom is the height of the trapezoid, plus the last trapezoid, which has base 1 and base 2 of 62, 55 over 2, and a height of 2. So we can cancel some stuff. Multiply that by 2. And we can cancel these 2's. Okay, so let's give it a shot. This is 193. I know it's over 2, but I want to add it with something else that's over 2. Plus 132 over 2. So 193 and 132 over 2 is 325 over 2. Let's see, we have 90 plus 73, that's 163 times 2, that's 326. And then we have 62 plus 55, which is 117. So putting these together, we have 443. This is going to be 162.5. So I guess we can just add those together, and we'll have something like 605.5. Now, that is the integral. That is the approximate integral. So we have 1 over 8 times, what was it? 605.5. Okay, so I guess we just divide that by 8. I mean, it might take you a little while to do it by hand. It's not too bad. I think it'll be something like 75.6875 or something. I don't know why I think that. Let's be very careful about it. I know that gives me 600. 5.5. So that's 6, because 48, not 56, goes into that. Then we have a 7. That's going to be an 8. Then we have a 6. That's going to be a 7. Yeah, okay. Should have trusted myself, but it's good to just make sure. So what this is it's an average temperature across the wire. So does it say to interpret what it is? Not really, but that is what it is. It means that the average temperature on the wire, obviously it's hotter where it's getting heated, and it's less hot where it's on the side where it's not getting heated. But the average temperature is 75.6875 degrees Celsius. That's the units of measure. Okay, part C. It's actually really easy. Find the integral of t prime and indicate units of measure. What is t prime? T prime is the change in temperature. If we're adding up a bunch of tiny changes in temperature over time, then we get a total change in temperature. That's all this is equal to. So this is just going to be, according to the fundamental theorem of calculus, this is just equal to T8 minus T0, which is the overall temperature change. So explain the meaning, we'll do that in just a moment. So this is just going to be 55. Oh, I see what it means. Explain the meaning in terms of the temperature. It means not just the change, because it's not over time. Sorry, I misspoke when I said it's over time. It's the change in temperature over distance from the point where it's heated. So in other words, it's just like the difference in temperature from as far away as possible from the heated end. So that's on this other end. It's the change in temperature from here to here, from these positions, rather than over time. So this is 55 minus 100, which is negative 45 degrees Celsius. So it's basically the difference in temperature. Across the wire from end to end. That's it. That's what it means. Indicate units of measure. We did. Yes, we did. And yeah, that's just true because of the fundamental theorem of calculus. Are your data in the table consistent with the assertion that t double prime is positive for every x? Interesting. T double prime, we have to think about that. That's the change in t prime, right? It's the derivative of the derivative. So first of all, what is t prime? T prime is telling us how fast the temperature changes as we're increasing our x value, which is just fancy talk for saying we're going from the heated end of the wire to the not heated end of the wire. As we're moving that way, we calculated or estimated one of the derivatives as like it's going down. The temperature is going down as you walk away from the heat source, which makes sense, right? You have your hand close to the flame, it's hot. You go further away from the flame, it's less hot. But the question is, and I kind of looked at that earlier and was asking this sort of question, how much is the decrease really changing by? This is saying that the decrease let me make sure I have this right. Since t prime is negative, but it's saying the second derivative is positive, they're saying that the change in temperature follows a concave up decrease, something like that. as opposed to a concave down. That would be t double prime is negative. This would be t double prime is positive. And it's claiming that that happens every x in the interval. So we need to look for some average temperatures and see if the average temperature, rather the change in temperature, we need to find some changes in temperature and find out if it's fluctuating at all, because that's what the second derivative would tell us, right? So we need to look at a couple of spaces where we can get the t prime and compare it. So let's see, on the interval from 0 to 1, that's just the way that I'm approaching it anyway. On the interval from 0 to 1, what is the t prime? We can say t prime is approximately -7 right there, right? Then from 1 to 5, t prime is approximately, subtract these, -23 over 4. So that's -6.25. Wait, -5.75, sorry. Then on 5, 6, you should have these written down, by the way, these different t prime approximations. For 5, 6, t prime is approximately -8. And this is in degrees Celsius per centimeter. So, did you keep track of what happened there? On the interval 0 to 1, the average was -7. Then on the interval from 1 to 5, the average was -5.75. But then on the interval from 5 to 6, the average was -8. So what that means is that the second derivative, or in other words, the derivative is increasing, but then it starts decreasing. And if the derivative is increasing, that means concave up. But if the derivative starts decreasing, that means concave down. So how would we write that exactly? How would we explain the answer? Because that's how we're going to get some points here. We have to explain that t prime of x equals -7 somewhere on the interval, I guess I should say, for some x. We don't know exactly where, but since that's the average temperature change, we know that that's the actual temperature change at some spot due to the mean value theorem. And this function is differentiable. So for some x on the interval from 0 to 1, we know that the derivative t prime is -7. Now we know that t prime is -5.75 for some x on the interval from 1 to 5, which means that the derivative increased, which means, t double prime is positive. So far, so good. However, the derivative does not continue to increase. The derivative is then -8 for some x value on the interval from 6 to 7. That's why we calculated these different average derivatives, because we know that since the average there, oh wait, is that -6? That is -6. Sorry, it still applies. The same logic still applies, but it should be -6. And that's from 5 to 6? Whoa, wait a minute. What am I writing for my intervals? Yeah, what am I doing here? I'm getting my 6s and my 8s and my 7s mixed up. Okay, on 5 to 6. Got it, okay. So because the derivative did not continue to increase, see, this is an increase, it went up by 1.25, but then the derivative went down. So this means that t double prime must have been less than 0. I shouldn't write a less than sign. I mean it like a like an arrow. Like therefore, with those two combined, that means that t prime is negative for some x on the interval from 1 to 6. We don't really know where, but somewhere on there. So this is false. I guess we can just say it. Assertion is false. Falso. Okay, so there we have it. This was a great problem to look at. I think part D was quite challenging, takes a little bit of brain power, and we also had to refer back to this fact that the function t is constantly decreasing, but it's also twice differentiable, so that's really important. That means that the derivative is smooth, there's no gaps, there's no sharp corners, and the second derivative is smooth, which is really helpful for this. I'm always going to say, use your units wisely. You have to use correct units whenever they're requesting them. And I'll also say this problem was a bit tricky because this was not happening over time, rather this was happening over a distance. So as you imagine moving away from the center, regardless of time, even if it was frozen in time, if you were to move along the wire from the spot where it was heated, that's really where the derivative is represented. So it's not a change over time, it's a change over distance away. I should say it's a temperature change over a change in position relative to where it's being heated. So it's kind of interesting. It's like as you walk away from the center, what's happening to the temperature. And it's also interesting that the second derivative was not positive. I thought it should be getting, the temperature changes should be, consistent as you go down the wire, but it turns out it's not consistent because the first centimeter away, you drop 7 degrees, and then later you drop less than 6 degrees, and then later you drop 6 degrees. So it's kind of weird that that would happen. You would think that it just gets like smoothly less hot as you go away, but I guess not. Okay, anyway, that's enough blab out of me. I think I took enough time out of your day on this problem. I'll see you guys next time in the void.